Okay, so up to now we have discussed the stack concept, and in the stack concept we have already discussed what is stack, how it is organized in the memory, how elements are actually inserted into the stack. We have not yet see the practical syntax of how practically the elements are pushed into the stack, and we have done the stack implementation concept. That means how stack is implemented. That means if there is a main memory, so there is another part of the memory located in our computer system that is used for stack, and the subroutine program actually stored into the stack memory location, or you can store the important data that may be used in your program execution after some time. Sequentially accessing of data is possible in stack. Okay, that means we have also discussed the concept that if the number is stored into the stack in this way, then you cannot access the number in a random way, just like in your main memory. So this is your auxiliary memory, okay, located isolated from your main memory. So we have also discussed that topic, that how stack is actually stored into the memory sequentially, and also you have to access the different elements of stack sequentially. That is the main concept behind the stack. That means it has an access restriction. Also we have also discussed the TOS concept. TOS actually called the top of the stack, and also in the technical term it is called the stack pointer. That means if element are inserted into the stack, the last element is actually pointing, top of the stack is actually pointing the last element of the stack. That is also equivalent to the stack pointer. That means stack pointer also a address that holds the last elements of the stack to be inserted. Okay, the first element inserted into the stack is becomes the bottom, and the last element inserted into the stack becomes the top. And the last point is, we discussed that a stack grows in direction of decreasing memory address. Decreasing memory address means we have inserted the memory in the stack. That means elements in the stack 1 2 3 4 like that. So if this memory address is 50, so the next memory address to be inserted is 49. That means stack is grows in decreasing memory address. That is the meaning of that. So now from there we will discuss today that the same concept, that how is stack pointer is located. Stack point, we have not used the term top of the stack. Instead of that we use the term stack pointer. So stack pointer is actually, suppose this is your stack. Okay, so we have considered a portion of the stack. So first element that is inserted into the stack is 43, and the last element to be inserted into the stack is minus 28. You can see that. So the first element that is inserted into the stack becomes the bottom element, and the last element that is to be inserted into the stack become the top element. So the element address, that means this element is actually residing into an address. That address is pointing by this stack pointer. So that is the meaning of the stack. And also you must remember, I have told several times that the stack memory address is residing apart from the main memory. It is not located into the main memory. That memory is actually reserved. You cannot access this memory space for another use. This space is actually reserved only for stack implementation concept. Okay, so this is your stack pointer register. In the 8085 microprocessor, the stack pointer register length is 16 bit, and if the machine length is different, or the machine is different, computer is different, then this address length is also different depending upon the machine. So your next wait. Okay, so next is your push operation. So what do you mean by the push operation? Push operation is actually happens if this is your stack. Okay, so whenever we have inserted the element one by one in a sequential manner into the stack, that inserting operation is actually called the push operation. Okay, so suppose we have inserted the element 1 2 3 sequentially into the stack. So the method by which we have inserted the elements onto the stack, that operation technically is called the push operation. So push operation is actually performed by two different method, or two different sub function is associated with the push method. That is, first is subtract and second is store. Now you can see that the instruction is subtract stack pointer by 4. So the meaning of this instruction is that we have decremented the stack pointer by 4. Whatever the current value of the stack pointer, suppose this is your stack pointer is pointing to the location, this is your stack pointer, and next the meaning of the 4 decreasing order is that if we insert the element in the stack, like first element to be inserted into the stack is 1, then okay, so two operations are associated with this push operation. First one is the subtract operation and second one is your store operation. So this, why these two is actually important, here you can see the stack pointer is decremented by 4 and new element has to be stored into the stack pointer, move new item to the stack pointer. So meaning of that, here first you consider, I have said that if the first element, this element first has to be inserted into the stack, so the stack pointer is actually pointing to the 50. If next element 2 is to be inserted into the stack, so the first operation you have to perform that, you have to decrement the stack pointer by 1. But here we have assumed that the length of the element that has to be inserted into the stack, the length of the element is 8-bit. Okay, and we have assumed here 8-bit machine, so that is no problem. One address is actually holding the 8-bit address, that is the meaning of the 8-bit machine. But if the machine is 8-bit, then this stack pointer would be decremented by 1 and then the stack pointer is pointing to 49 and new element is to be stored into the second memory location. That means the 2 is to be stored into the 49, that is the meaning. But if the machine is 8-bit and we want to store the 32-bit data, here we have assumed the 32-bit data. You can see that 32-bit data word length, we have considered 32-bit word length. So if the machine length is 8-bit, that means one memory location can at most store the 8-bit data, then we want to store the 32-bit data at a time, then the 4 memory location is actually holding the 32-bit data. So to store a 32-bit data at a time, we need, suppose the data is 1 2 3 4, that is the 32-bit data as a whole. So to store the 32-bit data in an 8-bit machine, we require 4 address. Okay, so the stored again a 32-bit data, we have to decrement it by stack pointer by 4, that means 1 2 3 4. After that, from 46 onwards we can store the next 32-bit data. So that is the meaning of the stack pointer is decremented by 1. So I am again repeating, if the machine is 8-bit and data is to be stored by 8-bit, then you have to decrement the stack pointer by 1 and you can store the new element at that location. But if the machine length is 8-bit and you want to store the 32-bit data on that machine, that one 32-bit data is requiring 4 address, so you have to decrement the stack pointer by 4 and then you can store the new data, new 32-bit data on that memory location. Okay, so here if the stack pointer first is pointing to the 50, then 1 2 3 4, this 32-bit data is stored at that 50 49 48 47 collectively, then from 46 onwards you can store the new 32-bit data. That is the meaning of that. That first push operation is performed by 2 operations. First one is the subtraction, that means stack pointer is subtracted by 4 and then the new memory new item is to be stored in that memory location. So that is the meaning of that. Okay, so this is the push operation. So next is your pop operation. So pop operation is just the reverse of the push operation. So in the pop operation you have to just, suppose this is your data 1 2 3 4, again we have considered the 32-bit data. So here the memory address is 50 and here the memory address is 50 49 48 47. So this is the data. So if the item is to be popped, then first we load the stack pointer. Okay, this is the pop operation, and then add the stack pointer by 4. That means we have incremented the stack pointer by 4. After popping this element, the stack pointer is pointing to 50. That means this stack is become empty. Okay, the stack pointer is pointing to 50. First of all, stack pointer is pointing to 47, and after popping this, popping means we are getting the data to a storing this data to a new memory location. That is the meaning of the pop. We are accessing that data. So after popping the data, stack becomes empty and the stack pointer is again pointing to 50. Okay, before that stack pointer is pointing to 47, and after the pop operation the stack pointer is pointing to 50. And obviously you must remember, here we have considered the machine length 8 bit and we are storing or popping the data that is 32 bit. So 32 bit data is actually requiring 4 address, so that's why +4 operation is actually performed. So that is the meaning of the pop operation. Next, wait 1 minute. So this is the effect of the stack operation. That means you can see that the stack pointer is after push from RJ, push into the RJ. That means this suppose this is your stack. Okay, so suppose this is your stack, originally stack. Okay, up to this, and you want to insert the element 19 into the stack, then you have to decrement the stack pointer by 1. Here the 8 bit concept is actually used, and you have to store the data 19 into the stack. And similar concept, you have to pop the data 19 from the stack, then you have to just increment the stack pointer by 1 and access the data, and after that this memory location becomes empty and the stack pointer is actually pointing to next memory location. Here the 28 data is 28 is to be popped, so 28 had been popped and this becomes empty, and this is the location where stack is currently pointing. So that is the meaning of, and here we have considered that means stack pointer is incremented by 1, so a machine length is 8 bit and the data is also 8 bit. That is the concept. That's why stack pointer is incremented and decremented by 1 in the case of the push and pop operation. Okay, next, and stack full or empty. So this is a different operation. That means whenever we want to store any data into the stack, that means suppose this is your stack and the stack is assigned. Suppose stack is assigned from this is the first memory location 50 and the stack is assigned up to memory location 40. Okay, so this is the length of the stack, and here we have assumed that all the element in the stack are full. Okay, all the element into the stack are full, so no new memory location are available for storing the data. So for checking that whether the stack is full or empty for the new data, then this instruction is actually used, compare instruction. So compare source and destination. So compare source and destination means we have actually checking this is source and this is destination. So this is the source address actually, and this is the destination address. So we are performing the subtraction operation, and depending on the carry flag we are checking this. Suppose this is your destination is your source is 50. Okay, and your destination is suppose your 40. So 40 is not available. So if this number is become negative or positive depending on the different carry flag, that means the subtraction operation, if the less the carry flag is generated, if subtraction operation is positive, there is no generation of the carry flag. So just by comparing these two address we can check whether we can insert the new element into the stack or not. That means stack is full or empty, we just checking that. That is the meaning of that. Okay, now we have previously discussed the compare instruction. So this compare instruction is used in this save push and this save pop instruction. Okay, so this is the series of instruction in the save pop operation. Now the pop operation is actually popping the last element from the stack. So whenever pop instruction is executed in a stack, first the stack pointer is incremented by 1 and the new item is to be moved to our desired memory location. That is the series of instruction in the case of pop, ordinary pop. Now in the case of the save pop operation, we first check whether the stack is empty or not, then we perform the move operation. Whether there is no element in the stack, then we get the empty error, and if there is a element, then we move this element to our desired location. So that is the meaning of this save pop operation. So suppose this is your stack organization. So bottom address is 2000 and the top address is 1500. Now suppose whenever this is suppose 1999, like that, here the value is 2, here the value is 1. So previously suppose here the stack pointer is pointing to here previously. Okay, so just ignore that. So stack pointer is suppose pointing here. So in the case of the save pop operation, whenever this instruction is executed, what happens is that the compare instruction is executed. Compare means this is your source and this is your destination. So actually from destination, source is actually subtracted. That is the meaning of that. So here destination address is 1999. So that is the meaning. So 1999 and your source address is 2000 and this has to be subtracted, and here the value is negative. If the value is negative, then this instruction is not executed. That means if this value is greater than 0, then the empty error would be flashing, and if this is not, pop operation is successfully performed. Now after performing this operation, the stack pointer is pointing to 2000. So again, if then we again the save pop operation, then 2000 minus 2000, there is 0, and again the element is to be popped safely. Okay, so after whenever performing this operation, the stack pointer is actually incremented by 1. Whenever this is pointing to, suppose pointing stack pointer pointing here, so this save pop operation is performed. After performing this save pop operation, stack pointer is incremented by 1. So after performing pop from this location, stack pointer is pointing to 2001. So whenever we again run after 1 2, then again run save pop operation, then what happens? The stack pointer is pointing to 2001, but there is no element there. So empty error will be generated. So empty error, stack pointer is 2001, so 2001 minus 2000, so positive value is generated and empty error will be flashed. So that is the meaning of the save pop operation. Save pop operation means first the stack is checked whether it is empty or full, then we perform the pop operation. And this is also true for the save push operation. So that is the same thing. Okay, so we have just draw the same figure for the case of the save push operation. So suppose this is your stack and suppose this is your different memory location. Okay, and the address of this here is 1500, as we have said that, and this address is 2000. Okay, and suppose this is 1501 1502, like that, and here the element is suppose 1, here the element is 2. Now suppose stack pointer is pointing to at that location. So what happens is that 1501, so here we compare 1500 and stack pointer. So stack pointer is 1501 and this is 1500 fixed, so value is positive. As the value is positive, so we can, suppose there is no element first, suppose there is no element, we want to insert 1 here. So if we want to insert 1 here, the stack pointer is actually first the stack pointer is pointing to that location. So the stack pointer is decremented, first the stack pointer is decremented by 1 and the new element is to be pushed here. That is the meaning of the push operation. Okay, simple push operation. First the stack pointer is decremented by 1 and then the new element is to be inserted. What? Suppose the stack pointer is pointing to 1501, so it is first it is decremented by 1, then the compare instruction is performed. So if this is positive, we can say that we can insert the element safely. There is a vacant space to push the element into the stack. So this is not less than 0, so full error will not be flashing. So we can safely move the new item into our desired memory location 1501 and the stack memory location is decremented by 1, that means 1500. Now again we perform the save push operation, then what happened? 1500 minus 1500 is 0, so it is again not less than 0, so we can not getting the flash error, this full error, and again we can safely push the element here. So while performing this operation, the stack pointer is actually moving to 1499 location. Now again, if we again run after inserting the element here, if we again run the command save push, what happens? 1499 minus 1500, so that is negative quantity. So you can easily say that there is a full error is been flashed here. So that is the meaning of the save push and the save pop. Here in these two we are just checking whether the stack is full or empty. For the if the stack is full, then we cannot insert any element into the stack. That has been used checked by this branch instruction. And if the stack is empty, we cannot pop any element out of the stack. That is also checked by this branch instruction. Thank you.